So, General Thomas, I think. I'm talking to a guy in our class. He's like for 30 years. And I've been talking to him. He works for radio right now. He's even told me at radio engineers are just when it comes to no one gets it, and so that's why when I tell you how you said how important
we're not going to fight about it, right? And so you ask
So, if you're in line at 125, and you're designing a bucket burger or the worst case, the average no. At least amount of current, so it's the largest load. Which is counterintuitive. You think the worst case would be the most current, right? It has to do with integrating continuous mode earlier when you have less current in your system. And John's work with designing, always thought that the worst case was what's the most current. And it's like when it comes to continuous mode, we get but even doing this, he doesn't like it. He doesn't so he didn't really say, oh, I didn't know that. He kind of, and the next time we talked about it, he had it right because I taught him. My master's degree is useless there. It's all about being
I'm going to go over this very quick. You have it in the homework 2, I believe. The last problem is similar to this one, but you have it 2 1. The one you have in the homework 2, last problem. Or I think the last 2 problems were about this rotating machine. Because I want to go over this one. See how it goes. So we have a machine, which basically is a synchronous machine, but I'm going to say now it's synchronous machine. But we have a machine, it has a one winding here on the rotor, and it has a stator. This stator also has another winding here, for example, right? This is the rotor, and that's the stator. Each of them, they're going to generate a magnetic field, right? What is the magnetic field? What's the direction of magnetic field for this one?
It goes inside of the
I don't know myself. I have to figure it out. But let's see. Let's forget this one, right? I have one winding here, right? The current is going out of board. Is coming out of board here, going to the board, right? I'm going to put my finger here where the current is like this, right? So, and here, if you put it again, so that here, in the middle is going to be like this, right? This one and this one, they're going to help. I have a one here, I call it Fs. Fs because this is a stator, this is a rotor. I call this one Fs, right? How about this one? And it's going to be, oh, this one is going to be perpendicular to here, right? This axis, right? Now let's look at the other one. The same thing, right? Here, flux going here, and here, flux going here, right? So this one also have another axis here. Sorry, we should cross here. We should cross here also, in the center. And this one is going to generate a flux like this. I'll call it Fr. You have two magnetic fields. One is Fs, one is Fr. Tell me now, I talked about this induction machine. What's the condition, under what condition this machine is going to rotate, this rotor is going to rotate? Tell me. No. How about those magnets we had in the way? They should move in the same state, right? So this one is rotating with omega r, and this one is rotating with omega s, right? This one has one frequency, that one has another frequency, right? Unless they have the same frequency, we're going to get there. That last is going to ask, tell me at what speed this machine can steadily run. See, this machine, as soon as you plug it into the wall, even if this two years and before, is going to rotate. But maybe it rotates 2 turns and stops. It doesn't. Or it starts to like do it, go a little bit this way, a little bit that way. You want kind of a steady state, you want to rotate it like 100 RPM this way, for example. Or I don't know, 200 RPM this way. That's the motor, right? That's something, it does like something like this, right? So, it's saying, let's say the rotor circuit, rotor is this one. This machine has this one. IR of T is IRM, that's the maximum value, cosine of omega RT plus alpha. And IST is ISM, and S stands for stator, R stands for rotor, is cosine of omega S. Initially, say the values are different. That one is omega R, this one is omega S. You know, we connect out one source, this one to another source, right? Actually, I give the example somewhere. In the problem we gave you, it's simpler than this one. But usually they tell you this. They said, let's put this angle theta. I'm going to explain, I can give you the inductance values like LSS, LRR, and LSR, but I'm going to explain to you why they are that much bad. Let's think about this one first. I'm going to go back. I have a circuit like this. So the question is calculate the torque for this circuit, the torque value for this circuit, and find out under what condition this machine is going to rotate, continuously. The steady is going to continue. Basically, for machine to rotate continuously, you have to have an average torque non-zero, right? If the average of the torque is not zero, means you have a steady torque, right? So the machine is going to rotate. The question is, say, calculate the torque equation for this machine, and after that, tell me under what condition this machine is going to rotate, continuously. Which means at what speed the average of torque is not zero, right? Now, before going there, let's look at this. I'm going to make you a machine designer now, because in homework 4, homework 2, or last problem, I gave you the values, right? If you look at it, I told you, MAF, there are 3 windings over there. There are 2 on the stator, 1 in the rotor. The rotor we call it F, like a field, and those one AF and A and B. It's a 2-phase machine. So I gave you MAF and MBF, and the rest they are going to be constant. I'll explain it why. You know, that one is a 3-winding machine. 3 winding. Remember on the problem number homework number 1. Problem 5. You had a 3-winding system, right? You have to calculate L11, L22, L33, L12, L13, L23, those kind of things. That machine is like that. It has a 3 windings. The only difference is this one is one part is rotating, that one is not rotating. It's stationary. Now let's look at it. How much is the L? This is the number. We have only 1 winding. How much is the L11? Or here I should say just F because there is just only one, right? So it is N2 over R, right? Does R change here? No. So basically L is a constant value, right? If I have an X parameter, I want to take a derivative. dl over dx is how much? 0. Why? Because the magnetic circuit doesn't change here, right? Let's say if this circuit was like this. I had a moving part here, right? Let's say this is perfectly fit here, you know, there's no gap here. But this one is moving. Is L here constant? Why? Because this value is changing, right? So when it's here, I have a different gap, right? This distance is fixed, but A is changing, right? Right? So this one, L is not constant, right? Now let's look at this one. It's like a let's put a 2-winding system now. Because this one is easier to imagine, no? Right? We have L11, L22, and L12 and L21, right? And let's say the system is linear, L12 and L21, they are the same, right? So is L11 variable here? Does it change? No. Because L11, let's say, get rid of this one, right? You get rid of this one, you calculate the reluctance and done. L22, you get rid of this one, and you calculate the resistance, right? So done. How about L12? How do you calculate L12? Let's mention that, you know. So we say if the lambda 1 is L11, right? I1 plus L12, I2, right? Lambda 2 is L21, I1 plus L22, I2, right? Let me make it easy here. You know L11 is very easy. You say, like, get rid of this one, whatever R I have, N12, you prove that one. But basically, you can say lambda 1, right? Divided by what? I1 when I2 is how much? 0, right? What's the lambda 1? N1 C1. We have 2 here, we should say. What's P1? P1 is here, right? So basically what you're going to do, you're going to get rid of this one, calculate the flux here, right? Times number of turns, right? Divided by I1 is going to be the equation already. It's going to be N1 to the power of 2 divided by 1, right? How about L lambda 2, L22? Right? Actually, let's use this opportunity to explain this one also. Right? Make this one 0. When 0 means this one is not here, right? This is a phi2. Either up or down. No, put it this way, it doesn't matter. The direction doesn't matter. We are going to go with the absolute value, right? So you calculate. How about L12? I'm going to use this equation. Or I can use this equation. It doesn't matter which way you want. You want to calculate this one should be 0. I don't want to have this one, right? So I'm going to say lambda 1 over I2, and then I1 is 0, right? What I'm going to do, this current is going to be 0. But here is important, careful. Let's say this one current was this one, I1, and this one I'm not sure which way. For example, it's I2 this way, right? Let's not be worried about the sign for now. So you get rid of this one. With having this one here, you calculate the flux here, right? But times by this number, you get how much? Lambda 1, right? Do you understand? I'm saying you put this winding here, you calculate the flux here, times by this number of turns, right? It's going to give you the lambda 1, right? Which is going to be a function of I2, right? There is no I1, right? And that I2 is going to cancel with this I2. If the system is linear, we are not going to see any I2, right? Now, you understand how to calculate the value. L21 is equal to this one also. You can use this one. You say lambda 2 over I1 when I2 is 0. They should be the same. Both of them should be the same answer. The only thing is the direction, the sign of L12 or L21. Let's say this current is like this, right? Originally the flux is here like this, right? This one is, I'm going to make it negative. Let's put it this way. Right? The flux here is going to be like this, right? The one is generating it here, right? If this one is not here, this flux, part of it is going to come here, part of it is going to come here, right? So this one, look at here, is opposite of what this one is generating by itself, right? So L12 is negative. L12 can be positive or can be negative, right? If the flux of this one and this one, they help each other, it's positive, right? If they are against each other, it's negative. So, you learn how to calculate L11, L22, about all those kinds of things. Now you got the question. Now I'm going to come back here. Oh, here, let's just take it, sorry. Because this is easier.
Are they both going to interfere with each other either way, even if they're going the opposite direction, like in the sensor?
They're going to interact with each other because in reality we have both of them here, right?
Yeah.
So they're going to help each other here in this leg or in that leg, or either here they're going to help here and here. For both of them it's going to be help, or for both of them it's going to be against each other, right?
Yeah.
So you can figure. Let's say I say okay, that one is not here. Flux is going to go this way, right? That's the easy way to figure it out. This one is not here. Let's say here. This one flux is going to be here, right? So this one is coming here, half is going to come here, half is going to come here, right? Nothing is going to come from here. Why? Because there is no winding, right? Now, look at here, L11, L12, L22, everything is fixed. Why? So the circuit doesn't change, right? The circuit doesn't change. Now let's look at the circuit. This air gap everywhere is fixed, right? Everywhere is the same, right? So over there we have an LSS, we have an LRR and LSR, right? LSS, LRR and LSR. I'm going to explain LSS and LRR. I'm going to tell you why LSS is a constant and LRR different. Right? Let's say why. Let's look at the, like here we talk. Let's think of the, for example, rotor winding, right? How is going to be like this, right? We have one winding here and one here, and I have a rotor here, right? What is going to happen? The flux, this one is going to generate, right? This one is going to generate flux. Flux is going to go like this, right?